we are, back for another update on the MegaIC Tester. The software is up to 5.9 now, and I've been concentrating mostly on developing the timing diagram functionality, speeding the thing up, and adding support for chips that share the same number but actually have different capabilities or I/O mapping depending on whether it's an LS or an S or an F or an H or what have you. So the first thing I'm going to do is I'm just going to pop a 74867 chip in, do an identify. It's 24. You saw how fast that was. That's because my Excel spreadsheet, which generates the database which is used by the MegaIC tester, I've now got it to generate one file per pin count. So there's one file for all the 20 pin chips, one for the 14 pin chips, etc. So if I just pop in, let's say this is, what's this then? I don't know what it is, that's the point, isn't it? So I'll stick that in. That's a 14 pin chip. Do an identify, 14 pins, and it's just rattling straight through them because it doesn't have to skip over all the pin sizes, all the chips, all the pin sizes. So it's a 74243. Okay, so if we pop the 74867 back in, it now finds it immediately when it wants to do the test, and that's because, as well as generating one file for each set of chips with the same number of pins, the Excel spreadsheet also generates one file per chip, and therefore when I want to find a chip I just have to open the file with that chip number. So here we are, we've got a synchronous 8-bit up-down counter. There's the diagram for it. We've now replaced the pinout button with an exercise button. That's because that's what you do if you choose that button. We've got the logic thing, which I'm still developing. We've now got the new timing diagram function. Okay, so what we've now got is this chip only has a single element on it. However, what the chip tester does is it says, okay, it's a single element, but in order to sort of categorize the pins, I'll make some control pins, so that's the ones in white. We've got input pins, we've got output pins, and if this chip had bidirectional pins, they would also be a different pseudo element, as it were. So for each pin, we get the name of it, we get it overscored if it's an active low pin. We see the timing diagram, we've got the pin number over here. So all the clock pins are in white, all the control pins are in white, all the inputs are in yellow, and all the outputs are in magenta. Now we can use this bar here to turn things on and off. So at the moment we can't see hardly any of the outputs. So if we actually turn off the inputs just by clicking here, that turns those off. So you might notice that the outputs are all thicker lines and the inputs and controls are all thinner lines. So this isn't meant to be a true representation of the timing of the test cases, because the clock is just a single pulse within a particular test case, and this diagram doesn't represent anything in terms of propagation delays, rise and fall times, or anything like that. It's just meant to represent how the test cases are applied to the chip. Now you may notice up the top here we've got the test case numbers, which are all color coded, and I'm using the resistor color code. So 1, 2, 3 are brown, red, orange, and so forth. And you might notice that some of them have got a slight underscore underneath them, like 4 has, but 5 hasn't, and 6 hasn't. And any that have an underscore under them actually have a test case description, and if we actually just poke the number, it will actually show us what that is. So that first step there resets all the inputs, sets all the input high and checks all the outputs are low, right? And if we actually look at number 4, that shows 3 clock pulses and check for correct outputs. Now that's going to take 3 steps altogether. That's 4, 5 and 6. 5 and 6 don't have an underscore under them because that's not a new instruction, but if we hit 5 we can still see what the actual test case is doing. It's actually being initiated at step 4. So that's a timing diagram for a chip with a single element. So if we pop that out and we pop in, let's say this one, which is our old friend, the 7402 with a missing leg, that X gets us out, and this E over here will flip it into exercise mode, but I haven't implemented that yet. So we'll do a test. Now this is slightly changed, but we'll come to that in a minute. 7402. So it's amber status because one of the elements has failed, and that's element number 1. Look at the timing diagram. Right, so this is a multi-element chip, so instead of showing controls, inputs and outputs down the side here, we've got one blob coloured in to line up with the 4 elements that we've got, and element 1 has failed. We can actually see here that it was okay on the first step, but then it failed for the next 3 steps, which is what that red thing there indicates. And again, we can just turn the elements off if we want to, or turn them back on again. So something you may have noticed is that, just putting a 7451 in here, if I do an identify on this, and it's a 14 pin chip, so it behaves like 3 different chips. Now, as well as purely numeric chip numbers, you can see here we've got a 74LS51, and you might think the 7451 and the 74LS51 would be the same, with the 74LS just being low power Schottky, but no, the 7451 actually is a dual 2-wide 2-input and NOR gate, and the LS version, even though it's got the same number just with LS in the middle, actually has 2 2-inputs and 2 3-input and NOR gates. So I've now enabled support for chips that have different pin layouts, even though they share the same chip number. So if we pick the 74LS51, this actually behaves like it, even though it is a 7451, and that's just down to the way that the chip is configured. But if we go, let's actually do a 7451. Okay, and we'll look at the timing on that one. Right, so on this one, these are the 2 input AND gates, and the outputs of those feed into this NOR gate. So because the output of element 3 is associated with elements 1 and 2, that's why we've got this double colour bar here. It's outlined in green and the line is green. So again, we've got thin for inputs and thick for outputs. Right. And if you want to utilise the facility where you enter, you've got one of those oddball chips, like the 7451 and the 74LS51, I've provided an FHLNS key down here, and that's because looking through the Wikipedia list of 7400 and 4000 and 4500 devices, FHLNS together cover all the ones that I could find that had those oddball characteristics where 2 chips with the same number have different middle letters that mean they have different functionality. So to enter 74LS51, it's just, and away you go. I've now popped a 74245 into the ZIF socket, and if we test that one, this is a transceiver, so some of the pins will be acting as inputs and also acting as outputs. And just to show you what that looks like on the timing diagram, we've got input outputs 1, 2, 3, 4, 5, 6, 7 and 8, and also input outputs A, B, C, D, E, F and so on. And what this shows is input output 1 actually goes to input output A. So in this case, because this line on A is thin, so we've got high in the first step, and that's going to input output 1, which is showing as a thicker line. So these inputs all the way up to step 5 are being manipulated on input output A and reflected on input output 1, and you can see that because the enable pin, which is active low, is raised here, the outputs on the transceiver are disabled and therefore go into high impedance state, and that's why we've got a thick output line that's high, then low, then goes to high impedance state, then goes back to high, then back to low, and then because the direction pin flips from low to high, this input output then becomes an input, and down here input output A then flips from being an input to being an output, and again we've got the high impedance state being implemented by the enable line going high. Because I've now got rid of the index, because I'm just generating the pin count specific files and one file per chip, we no longer have a re-index button. However, we do have a stats button, and if we poke the stats button, what it's going to do is it's going to go through all of the pin count specific chips, scanning 14 pins, and 16. And as you can see, it's showing us the pin count, how many ICs there are, how many have got details, how many have got symbols, and how many I have personally tested. So there we are, 208 chips, 207 with details, 187 with symbols, and I've tested 117. I'm still adding stuff to the database as I go along, but I've been spending most of my time on development. Something I didn't show you with the 74867 on the timing diagram. So these are normal test cases where the inputs and controls are applied and the output is checked. However, if we scroll further across and look at more of the test cases that are applied to this chip, steps 21 and 22 are multi test cases. So if we actually look at the definition of 21, it says do a full range count from 0 to 255 and check carry goes low. So what we've got here is the controls, the clocks and selects and enables are shown, the inputs are all shown. If we actually hide the inputs and look at the outputs, all the outputs are hidden during this step because the controls and the inputs are being applied to the chip 255 times, but the outputs are not being checked until the second phase of the test. So here we've got in step 21, we're applying a clock pulse, we've got select 0 and 1 high, we've got enable P and enable T low, and we then expect all of the outputs to be high apart from the ripple carry out, which is active low, and we're expecting that to be low. It then, on test case number 22, we're going to do 255 counts and full count of 255 to 0, check the carry goes low. So again, we're applying the clock, select 1 is now low, which causes it to go into countdown mode. We're then applying the the inputs 255 times, and then what does that do with the outputs? That then makes all the outputs go low and ripple carry out. So that shows how we can show multiple tests even on the timing diagram. Right, the next thing I'm going to implement is the, let's show you. So for version 6, I'll be concentrating on the logic diagram view of the pins, and I've got a few other things up my sleeve. Right, hope you enjoyed that. Bye bye.